Hi, I'm Norman Wildberger. Today we're going to prove the triangle spread rules. This lecture is going to be more technical than usual, and in fact I admit that probably the proofs that I'm going to give you today are not very optimal. These are the only ones I've been able to come up with, and perhaps some of you will come up with simpler arguments. So the triangle spread rules concern the three spreads of a triangle, which we know satisfy the triple spread formula. And they are that the spread S3 is the big solution of the triple spread formula precisely when S1 and S2 are acute. And secondly, S3 is obtuse precisely when S1 and S2 are acute and S1 plus S2 is less than or equal to 1. So I remind you that as a quadratic equation in S3, this triple spread formula has two solutions. And there's a little one and a big one, only distinguished by this negative sign and this plus sign. So if we're given S1 and S2, there are two possibilities for S3, and the first one tells us which of those two possibilities to choose. And I remind you that the spread S1 being acute is equivalent to the condition that S2 plus S3 is bigger than or equal to S1. So we want to prove these things. All right, let's start with the first triangle spread rule, which says that S3 is the big solution of that quadratic equation precisely when S1 and S2 are acute. When we want to prove something like this, we have to go in both directions. We have to show that this implies this and that this implies this. So there's two steps to the proof. So first we're going to assume this, that S3 is given by this big solution. Then if we add S2 to both sides, then we get S3 plus S2 is S1 plus 2 of these, and there's also a 2S2 here, so we factor it as 1 minus S1 plus 2 times this. And S3 plus S2 is going to be bigger than S1 because this is positive and this is positive. And there's an S1 there. And that's telling us that S1 is acute because that's the condition that S1 be acute, that S3 plus S2 is bigger than or equal to S1. So we've shown that S1 is acute, and similarly S2 is acute because S1 and S2 are playing symmetrical roles. Now conversely, suppose that S1 and S2 are acute, so we know these two relations. And let's suppose that S3 is actually the little solution. So we want to prove that's wrong. So there's the little solution with a negative sign there. And now we look at S3 plus S2 bigger than or equal to S1. That's, we know, is true because S1 is acute. So there's S3. If we add S2 to it, we get S1 plus 2S2 minus this, and that's supposedly bigger than or equal to S1. And that tells us that S2 minus S1 S2, because we cancel the S1s and then divide by 2. So we have an S2 here, a minus S1 S2, and we bring this stuff to the other side. So we get this inequality. So that's the equality we've just established. We square it, and then some things cancel because the S2 and that S2 cancel. 1 minus S1, which is positive, will cancel with that. And so we get S2 times 1 minus S1 is bigger than or equal to S1 times 1 minus S2. When we expand that and cancel the S1, S2 from both sides, we get that S2 is bigger than or equal to S1. But S1 and S2 are playing a similar role, so similarly S1 is bigger than or equal to S2. And these two inequalities show us that then S1 has to equal S2. Okay, but then we go back to the original formula for S3, and we get S3 in terms of simply S1. And when we work that out, then what we see is that it all cancels and we get 0. So as a consequence of S1 equals S2, it means that S3 is 0, and that's impossible. So our assumption that S3 is the little solution is wrong, and we're forced to conclude that the big solution is the right one. So that proves the first triangle spread rule. And here's the second triangle spread rule, that S3 is obtuse precisely when S1 and S2 are both acute and S1 plus S2 is less than or equal to 1. So how do we prove that? Well, first of all, we're going to rewrite the triple spread formula in this particular way. This is simply some magic that I'm pulling out of a hat. So it's just a rewriting of the triple spread formula. And I remind you that S1 being acute is equivalent to S3 minus S1 plus S2 bigger than or equal to 0. Similarly for S2. And S3 being obtuse is equivalent to S3 minus S1 plus S2 being bigger than or equal to 0. So we have to prove this. Let's prove this direction. So we'll assume S1 and S2 are acute and that we have this inequality. And now we'll argue by contradiction. We'll assume that S3 is actually acute. Try to get a contradiction. How do we do that? Well, we look at this formula called star. The right-hand side, this is going to be positive because S1 is acute, and so is this one. This is always positive because the spread is always between 0 and 1. If S3 is acute, then S1 plus S2 is bigger than S3, so this is also positive, so the right-hand side is strictly positive. The left-hand side, well, this term here will be positive because of this assumption, but this term will be negative because we're assuming S3 is acute. So the left-hand side is negative. So that being negative, that being positive, that can't work. That's a contradiction. It contradicts our assumption that S3 is acute, so we conclude that S3 is obtuse. So this implies this. And in the other direction, assume that S3 is obtuse. Then we know that S1 and S2 have to be acute because a triangle can't have two obtuse sectors. If S1 plus S2 happens to be bigger than 1, then the left-hand side of that equation star is going to be less than 0. And the right-hand side, if you expand it all out, is this expression here. So that's going to have to be 0, less than 0 as well. But this can be rewritten as S3 times S1 plus S2 is less than S1 minus S2 all squared. And that's impossible because S3 times S1 plus S2 is bigger than or equal to S1 plus S2 all squared. Whereas that's because we're assuming S3 is obtuse, so S3 is bigger than S1 plus S2. And this quantity is always bigger than this quantity, so this contradicts that. And so we conclude that our assumption was wrong, so S1 plus S2 has to be less than or equal to 1. Okay, I admit that was fast and furious. The details are in my book. Don't worry too much about if you can't follow it all. It's not really crucial. The crucial thing is that these triangle spread rules are valid. Next time, we're going to have a quiz. We're going to have a chance to practice some more rational trigonometry in real life situations. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.